Today we get to delve into stats a little bit. We start with definitions for two measures of central tendency, mean and median. Measures of central tendency are typically the numbers given to best represent a sample. It's really common for us to use the mean or average to describe the sample. We just add up all the values and divide by the number of values we had. You've probably done this countless times already. Notice that there are two variables that are indicated for mean. Mu, which is the upside down H-like letter, and that indicates a population mean, and X bar, which would indicate a sample mean. Mean works great for normally distributed data. However, the mean, while often a fair representation of data, is not always the best data when data isn't normally distributed. For example, in my neighborhood, there are probably 400 homes that range from 50,000 up to 450,000, with an average and a median of maybe 230,000, maybe in a house like that. We also have Longwood Drive, where there's maybe 50 homes, but they average like 1.5 million. This picture actually isn't of any of the Longwood Drive homes. None of those are listed on Zillow right now. The average for the whole neighborhood might be close to 390,000, but nearly all of the houses are significantly less than that, while the median remains close to 250,000. In that case, the median gives us a better picture of what a typical house in the neighborhood might look like this one across the street from Professor Baker. Median is really resilient to outliers, and so can be really valuable for non-normally distributed data. We also need to indicate the precision of our data, which we do with measures of spread. I've already told you that the standard deviation is often our standard metric of precision. Standard deviation is calculated two ways, depending on if you're measuring an entire population or if you're only sampling it. If you're measuring the entire population, we use the sigma calculation, which is on the left. An example would be the census data, which should be at least close to the entire population. If we're only sampling the population, like a poll, there's more uncertainty, and we divide by the number of samples minus 1 instead of just the number of samples. Careful attention shows that the higher n gets, the less difference there is between these two numbers. I used two actual people populations, but the population could just as well indicate all the possible 10 milliliter samples you could get from a pond, or all the 10 gram samples you could get from a target soil area. And hopefully it's clear that if you sample the entire pond, you're going to get a better indicator of the average and standard deviation than if you just sample a few portions. Range is also a really common measure of spread. If you were measuring lead in drinking water, you would care about the median amount and the average amount, but it might also be valuable to see the range. A municipal water consumer might be happy to see average and median values of around 2 parts per billion or so, but they might also really care to see if there are outliers in the 800 parts per billion range, like what happened in Flint. Seeing range numbers can be a justice issue too. There's a good chance that the top of that range is going to include some of the poorest people. So as Christians, that number really matters. When we have larger averages, we'd expect to have a larger variation as well. We can normalize the standard deviation to the mean by using relative standard deviation. Notice again, there are two forms of this, sigma over mu for population and S over X bar for sample. These are often expressed as percents rather than decimals, in which case we'd multiply by 100%. Our final measure of spread is variance, which is just standard deviation squared. We use our measures of central tendency, mostly the mean, as a way of defining the types of error that we might see in an analysis. We do this with either absolute error, the difference between the measured mean, X bar, and the true population mean, mu. If the measured mean is greater than the true mean, the error would be positive. If it's less, the error is negative. More often, though, we'll scale the error based on the true value by dividing the absolute error, X bar minus mu, divided that by the true value, so X bar minus mu over mu, and then we'd report that as a percent. We'd call it percent relative error. This is the standard for indicating accuracy of our measurements. In Lab 1, you just report it as percent error, but you've already done this calculation. There are many types of determinate errors, that is, non-random errors, that could occur. Because they aren't random, they affect accuracy and not precision. The first type of error happens in sampling. If the samples aren't representative, we'll never get the true value. The second is a method error. Like if you don't tear the scale with the lid closed, it will always read incorrectly, and it will always read incorrectly in the same direction. If the signal from a pH meter has drifted, the readings may be systematically high or low, another example of that method error. Measurement errors are more insidious. If you have a volumetric flask that has a tolerance, the actual error from that flask will be in that tolerance range, but it will always be in the same magnitude and direction. The same volumetric flask is either going to be over or under the value as long as you're measuring it correctly. If you measure with the same volumetric flask every time, you will end up with all of your errors in the same direction, even if you're measuring correctly. Finally, there are personal errors. This could be the error from not looking directly across a graduated cylinder when you measure, an error called parallax. It could also be over-titrating when the color indicators are used because you can't see color as well. I have to be really careful about that one. It could be that you just aren't doing it right. Determinate errors usually have a definable source and are therefore preventable. If you can't find the source of an error, you can still work to minimize it. If your error is constant, that is, your error is always the same absolute size, you can often take larger samples. Any constant error can be dwarfed by a much larger sample size because while the absolute error will stay the same, the percent error will drop. If the error does change with scale, it's considered proportional error. Generally, we can control these proportional errors by using reference materials and calibration. For example, we occasionally check our scales against 100-gram reference standards to make sure that we're reading consistently across the entire range of the scale. For concentration methods, we might take readings of known concentrations of materials, and we usually do that every time to calibrate the instrument. The other types of errors are indeterminate. We can't determine what the cause is or what direction the errors will be and how they will affect the reading. Because these errors are distributed randomly, they won't affect the accuracy of the experiment, but they will affect the precision. And because we don't affect the accuracy, we often don't call indeterminate error at all. We call it uncertainty. We talk about two types of situations that we look at indeterminate error. The first is repeatability. If you did everything the exact same way, using the exact same equipment in the exact same space, you'd still get a variation. That variation is the repeatability. The lower it is, the more repeatable the measurement. If you took those measurements at a different time or in a different place or with different equipment, you would get a less precise measurement. We'd use that precision to indicate how reproducible it is, and it would always be less reproducible than it is repeatable. It might seem like that's worse, but reproducibility actually is a better measure because it takes into account some of the determinate errors within a lab, like temperature variations or variations in glassware, and even some minor user errors. It's hard to measure reproducibility in research because it means that someone else has to be trained on what you do and then do it someplace else. But in standard methods, many labs will be performing the exact same analysis, and reproducibility becomes actually really easy to measure. As we're learning, we will mostly be defining the repeatability rather than the reproducibility as you take replicate measurements and define the standard deviation for your measurements. When we take real measurements, we, in chemistry, will never measure the entire population. And we know that the population has a predictable distribution. Some values will be high and some values will be low. The problem is we don't really know the population standard deviation either, since we're limited by our ability to test. So instead, we're going to estimate how far off our measured mean, indicated as x bar, is likely to be from the population mean. To do this, we use a calculation called the standard error of the mean, indicated as S subscript m. The standard error of the mean is a measure of accuracy, even though the calculation involves and looks like the standard deviation. The idea is that if you know that you're taking a limited number of samples, indicated by n, and you're seeing variation in the values, indicated by the standard deviation S, you know that there's at least some random chance that all of your samples are high or all of your samples are low. They're not going to be perfectly distributed across the mean, just because you haven't sampled everything. So if we want to get better numbers, we really have two options. We can either make the sample standard deviation lower by improving precision, or we can increase the number of samples that we take. Note that these don't affect the standard error evenly. The standard error goes down with improvements to precision more than it does with an increase in the number of samples, because the increase in the number of samples is under the square root. Even if you don't memorize the math here, this is useful descriptively. More precise measurements improve accuracy because we have limited samples, and it takes incredible increases in sampling to overcome that poor precision. It's important to realize that error and uncertainty are not the same. Error is problematic because it actually gives you the wrong value. Uncertainty gives you a range of possibilities for values that should include the right value. A high uncertainty isn't inherently problematic. You can still know something about the sample, but the higher the uncertainty goes, the less valuable that information becomes. When we have uncertainty in one measurement, it may be easy to define. However, many values come from multiple measurements, like density or sums. Because the uncertainties happen randomly, it is unlikely that both uncertainties will be at their full magnitude in the same direction. They're usually at either partial magnitudes or in opposite directions. So the uncertainties in measurements are not added directly, but are scaled. Notice that for addition and subtraction, it's essentially like finding the hypotenuse based on the absolute uncertainty. So the absolute uncertainty of A squared plus the absolute uncertainty of B squared, you take the square root, and then that value would be the length of the hypotenuse of lengths uncertainty of A and uncertainty B. You can actually do the same thing with relative uncertainties for multiplication and division. If we do have multiple functions that we have to do, we would propagate uncertainty according to the order of operations. And so we're going to be focusing our next class on actually doing some of these propagations of uncertainty, so we can do them together.